there is a star in the southern sky that has already tried to destroy itself once. It failed, and the debris from that failed explosion is still expanding outward at over 1,000,000 miles per hour, forming a shape that astronomers call the homunculus nebula, two vast, ghostly lobes of gas and dust, hurtling through space, stretching nearly a full light year from end to end. A relic of an eruption so violent that for a brief time, this star became the second brightest object in the night sky, brighter than every other star in the heavens except one. And yet, against all expectations, it survived. Its name is Eta Carinae. It sits roughly 7,500 light-years away, deep within the Carinae Nebula, one of the largest and most active star-forming regions in our galaxy. It is not a small star. It is not even a large star. It is one of the most massive and luminous stars ever observed in the Milky Way, radiating roughly 5 million times the energy of our Sun. 5 million. That number is difficult to process, so consider this. If you could somehow line up 5 million of our suns and add their light together, you would only just match what Eta Carinae produces on its own. Every second of every day, it pours out more energy than our Sun will generate in an entire year. It burns with a ferocity that seems almost impossible, almost reckless, as though the star itself is in a hurry to reach its own end. Stars like this are not supposed to exist for long. The physics of stellar evolution makes that abundantly clear. The more massive a star, the faster it burns through its nuclear fuel. Our Sun has a lifespan of roughly 10 billion years. A star with 10 times the Sun's mass might last 20 million years. A star with 50 solar masses might survive for a few million. And a star like Eta Carinae, with over 100 times the mass of the Sun, might last just 3 million years from birth to death. In cosmic terms, that is nothing. A blink. A flicker. A candle that blazes so hot and so bright that it melts its own wick before the evening is over. And right now, that candle is nearing the end. Eta Carinae is unstable. It has been unstable for centuries, perhaps for millennia. It has already thrown off somewhere between 10 and 40 solar masses of material in a single eruption, an event that occurred in the 1840s and was witnessed by sailors, navigators, and astronomers across the entire southern hemisphere. That eruption released nearly as much energy as a supernova, the explosive death of an ordinary massive star, and yet Eta Carinae did not die. It endured. No one fully understands how. No one fully understands why. And no one can say with certainty when the next eruption or the final explosion will come. It could be in 100,000 years, it could be in 1,000. It could, conceivably, have already happened, the light of its destruction racing toward us at 300,000 kilometers per second, still centuries or millennia from reaching our telescopes. What astronomers do know is this. When Eta Carinae finally detonates, it will produce a hypernova, an explosion so catastrophic that it will outshine the entire Milky Way galaxy for a brief, blazing moment. For weeks, perhaps months, it may be visible in broad daylight, a point of searing light in the southern sky that refuses to fade. The blast will send shock waves rippling through the surrounding nebula, sweeping up the debris from earlier eruptions and accelerating it to even more extreme velocities. The radiation from the explosion will sterilize any planetary systems within several hundred light years, and depending on the orientation of its rotational poles, it could fire a focused beam of gamma radiation across interstellar space, a beam capable of stripping the ozone from a planet's atmosphere at distances of thousands of light years. We are 7,500 light years away. That is far, but in the context of a gamma ray burst, it may not be far enough. There is a term that astrophysicists use for stars like this. They call them time bombs. Not because the comparison is dramatic, though it is, but because it is accurate. Eta Carinae contains within it all the conditions necessary for one of the most powerful explosions the universe can produce. It has the mass, it has the instability, it has the luminosity pressing against the Eddington limit, and it has a history of violent outbursts that suggests the countdown, whenever it began, is advancing. The only variable we cannot read is the clock. By the end of tonight, you're going to understand what Eta Carinae is, why it behaves the way it does, why scientists believe it is approaching the end of its life, why its death will be unlike anything else in modern astronomical history, and what it means for us here on Earth, sitting in the gallery of the cosmos, watching a star that has already shown us what it is capable of, and wondering whether the next act will be its last. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand Eta Carinae, you first have to understand what a star actually is. Not in the poetic sense, in the physical sense. A star is a sphere of plasma, an incredibly hot gas made up of charged particles, held together by its own gravity and sustained by nuclear fusion reactions occurring deep in its core. Hydrogen atoms are crushed together under unimaginable pressure and temperature. They fuse into helium, and in doing so, they release energy. That energy pushes outward, pressing against the weight of the star above it. Gravity pulls inward, trying to compress the star further, and the star exists in a delicate, fragile equilibrium between these two opposing forces. Remove one, and the star either collapses or explodes. This balance between radiation pressure and gravitational collapse is the beating heart of every star in the universe. It is what allows stars to burn for millions or billions of years, and it is what determines, ultimately, how they die. Our Sun is a fairly ordinary example of this process. It has a mass of roughly 2 nonillion kilograms, a number so large that writing it out would require 30 zeros after the 2. It is approximately 864,000 miles in diameter, which means you could line up about 109 Earths across its face and still have room to spare. Light takes about 8 minutes and 20 seconds to travel from its surface to where we sit. It fuses roughly 620 million metric tons of hydrogen into helium every single second, converting approximately 4 million metric tons of matter into pure energy with each passing heartbeat. And it has been doing this, without interruption, without complaint, for approximately 4.6 billion years. 4.6 billion years. That is roughly 1/3 the age of the entire universe. Our Sun was born when the Milky Way was already 8 billion years old. Dinosaurs appeared on Earth only 230 million years ago. The entire history of modern humans fits inside the last 300,000 years. The Sun has been burning for 15,000 times longer than our species has existed. Now consider scale, because scale is everything when discussing objects like Eta Carinae. If you could shrink the Sun down to the size of a basketball, the Earth would be a small peppercorn, barely 2 millimeters across, sitting about 26 meters away. Jupiter, the largest planet in our solar system, would be a marble, roughly 1 centimeter in diameter, positioned approximately 135 meters away. Neptune, the outermost major planet, would be a small bead over 800 meters away from the basketball Sun, and the nearest star, Proxima Centauri, at a distance of 4.2 light-years, would be another basketball sitting approximately 6,700 kilometers away. That is roughly the distance from New York City to Tokyo. 2 basketballs, one in New York, one in Tokyo. That is how far apart the nearest stars are when scaled down to objects you can hold in your hand. That is the scale of just our local neighborhood in the galaxy. 2 adjacent houses on a street that spans an entire continent. There is another way to appreciate the difference in scale between our Sun and Eta Carinae that involves time rather than space. Light travels at roughly 300,000 kilometers per second, or about 186,000 miles per second. At that speed, it takes light approximately 1.3 seconds to travel from the Earth to the Moon. It takes about 8 minutes to reach us from the Sun. It takes roughly 4 hours to reach Neptune, the outermost major planet, and it takes 4.2 years to reach the nearest neighboring star. Now consider the Carinae Nebula. Light from Eta Carinae, traveling at the fastest speed the universe allows, takes roughly 7,500 years to reach us. The photons arriving at your eyes tonight, or at the sensors of a telescope pointed at the Carinae Nebula tonight, began their journey around 5,500 years before the Common Era. They left the star when agriculture was just taking hold in Mesopotamia. They travelled through the void while civilizations rose and fell, while languages were born and died, while the entire history of human thought and culture unfolded on a small, rocky planet orbiting a modest star. And now, tonight, After traveling roughly 70 quadrillion kilometers, those photons complete their journey, landing on a detector or a retina, carrying information about a star that may no longer exist in the form they left behind. This delay between emission and detection is more than a curiosity. It is a fundamental constraint on our ability to predict what Eta Carinae will do next. We are always 7,500 years behind. Whatever the star is doing right now, at this very moment, we will not learn about it for 75 centuries. If it has already begun its final collapse, the information is on its way, but it has not yet arrived. We are, in a very real sense, living in the star's past, and it is living in our future. The Milky Way contains somewhere between 100 billion and 400 billion stars, spread across a disk roughly 100,000 light-years in diameter and about 1,000 light-years thick in most regions. Our solar system sits about 26,000 light-years from the galactic center, roughly halfway out from the core in one of the spiral arms. We orbit the galactic center at a speed of approximately 514,000 miles per hour, which sounds fast until you realize that even at that speed, it takes us roughly 230 million years to complete a single orbit. This period is sometimes called a galactic year. Dinosaurs were just beginning to appear on Earth the last time our solar system was in this part of the galaxy. The entire age of the dinosaurs, from the Triassic to the mass extinction 66 million years ago, lasted less than one galactic year. Within this vast structure, stars come in an enormous range of sizes, temperatures, and luminosities. The smallest are red dwarfs, dim and cool, with masses as low as 8% of the Sun's mass. These stars burn their hydrogen fuel so slowly, so efficiently, that some of them will shine for trillions of years, far longer than the current age of the universe. They are the misers of the stellar world, hoarding their fuel with extraordinary patience. At the other extreme are the blue hypergiants and luminous blue variables, stars so massive and so luminous that they challenge the very limits of what physics allows. Stars that burn through their fuel in a few million years and die in violent explosions that can outshine entire galaxies. Eta Carinae belongs to that extreme category. It is among the most massive stars known in the Milky Way. Current estimates place the mass of Eta Carinae's primary star at roughly 100 to 120 solar masses, meaning it contains 100 to 120 times as much material as our entire Sun. Some models suggest it may be closer to 150 solar masses, though the uncertainties are significant because the star is hidden behind the dense gas and dust of its own making. Measuring the mass of a star you cannot directly see is extraordinarily difficult, but mass alone does not tell the full story. What makes Eta Carinae truly extraordinary is its luminosity. At approximately 5 million solar luminosities, it is one of the most radiant objects in the entire galaxy. To grasp what this means, consider a second-scaled comparison. If our Sun were a single 60-watt light bulb, Eta Carinae would be the equivalent of 5 million 60-watt light bulbs, all burning simultaneously in a single point of space. That is enough light to illuminate a small city, compressed into a sphere roughly 100 times the diameter of the Sun. If you were to place Eta Carinae where our Sun is, at the center of our solar system, the Earth would not simply be uninhabitable, it would be vaporized. The intense radiation pressure would strip away the atmospheres of the inner planets within minutes. Mercury, Venus, Earth and Mars would be bathed in a flood of ultraviolet, X-ray and gamma radiation so intense that their surfaces would be sterilized and their rocky mantles would begin to melt. Even Jupiter, nearly 5 times farther from the Sun than Earth, would be fundamentally altered by the onslaught of radiation. The concept of luminosity is important here, so let us be precise. Luminosity is not the same as brightness. Brightness is how much light you perceive, and it depends on how far away you are. A flashlight held in front of your face is bright. The same flashlight seen from a mile away is faint. But the flashlight's luminosity, the total amount of energy it emits per unit of time, has not changed. Luminosity is an intrinsic property of the object. It does not depend on distance. It is a measure of the total power output, the total energy emitted every second in all directions. Eta Carinae's luminosity is so extreme that it approaches what physicists call the Eddington limit. a theoretical boundary named after the British astrophysicist Sir Arthur Eddington, who first described it in the early decades of the 20th century. Eddington was one of the greatest minds in the history of astrophysics. He was the first to propose that stars are powered by nuclear fusion. He led the 1919 solar eclipse expedition that confirmed Einstein's general theory of relativity, and he derived the mathematical relationship between a star's mass and its maximum possible luminosity, the point at which the outward pressure of radiation begins to overcome the inward pull of gravity. The Eddington limit is the maximum luminosity a star can sustain while remaining gravitationally bound. Beyond this limit, the star cannot hold itself together. Its outer layers are literally blown away by its own light. Photons, the particles of light, carry momentum. When enough photons strike the atoms in a star's outer layers, they push those atoms outward faster than gravity can pull them back. The result is catastrophic mass loss. Material is ejected at hundreds or even thousands of kilometers per second. The star sheds mass in violent eruptions, creating expanding shells, rings, and nebulae of gas and dust. Eta Carinae lives at the edge of this limit. Some astronomers believe it has already exceeded it on multiple occasions, which would explain the great eruption of the 1840s. The star is, in a very real sense, tearing itself apart from the inside. Its own light is its own worst enemy, pushing against the fragile envelope of gas that gravity is desperately trying to hold in place. To put the energy output in yet another perspective, imagine a bonfire. A normal campfire at a summer gathering might produce a few kilowatts of thermal energy, enough to warm your hands and cook a meal. Our sun, if it were a bonfire, would be producing 3.8 times 10 to the 26th watts, a number so large it has no intuitive meaning. Eta Carinae, by comparison, would be producing roughly 5 million times that amount. The difference between our sun and Eta Carinae is greater than the difference between a birthday candle and a wildfire consuming an entire continent. It is a difference not just of degree, but of kind. These are fundamentally different categories of object. The energy budget of the Eta Carinae system helps put the star in context relative to other objects in the galaxy. The total luminosity of the Milky Way, the combined light of all its hundreds of billions of stars, is estimated at roughly 40 billion solar luminosities. Eta Carinae, at 5 million solar luminosities, accounts for roughly 1/8,000th of the entire galaxy's light output. A single star, one of hundreds of billions, producing a measurable fraction of the total light of the galaxy. If you could somehow remove Eta Carinae from the Milky Way, a sufficiently sensitive instrument in a neighboring galaxy might be able to detect the difference. This is the regime of stellar physics where intuition fails and only mathematics can guide us. The numbers are so large, the energies so extreme, the scales so far removed from everyday experience that our evolved cognitive equipment simply cannot process them in any meaningful way. We evolved to understand the world of the African savanna, a world of distances measured in kilometers and timescales measured in seasons. The universe of Eta Carinae operates on an entirely different plane of existence, one that we can access only through the abstract language of mathematics and the careful, painstaking work of observation. But there is another complication, one that makes the system even more difficult to understand and even more dangerous. Eta Carinae is not a single star, it is a binary system. Two stars, locked in a gravitational embrace, orbiting a common center of mass. In 1996, observations from the Hubble Space Telescope and ground-based spectroscopy confirmed what had been suspected for some time. Eta Carinae has a companion star, designated Eta Carinae b. This companion is itself a massive object, estimated at roughly 30 to 80 solar masses, depending on the model used. It is a hot blue star in its own right, luminous and powerful, though overshadowed in every way by its monstrous partner. The two stars orbit each other in a highly elliptical path, meaning their distance varies dramatically over the course of each orbit. The orbital period is approximately 5.54 years. At their farthest separation, called a pastron, the two stars are roughly 30 astronomical units apart, about the distance from the Sun to Neptune. At their closest approach, called periastron, the companion plunges deep into the extended atmosphere of the primary star, passing within roughly 1.5 astronomical units. roughly the distance from the Sun to Mars. The orbit is not a gentle circle, it is a wild, swooping plunge, bringing the companion star screaming through the outer envelopes of the primary at tremendous speed. At periastron, the stellar winds of the two stars collide with immense force. The primary star drives a dense, slow wind outward at roughly 500 kilometers per second. The companion drives a faster, thinner wind at roughly 3,000 kilometers per second. When these two winds meet, the kinetic energy of the collision heats the gas to temperatures of hundreds of millions of degrees, far hotter than the cores of most stars. This collision zone generates intense X-ray emission that astronomers have been monitoring with the Chandra X-ray Observatory since 1999. The X-ray observations have been revolutionary. They revealed that the system undergoes a dramatic X-ray minimum, a sudden drop in X-ray brightness at each periastron. This minimum lasts roughly 3 months and is accompanied by changes across the electromagnetic spectrum. The leading explanation is that at closest approach, the dense wind of the primary star envelops and smothers the companion, snuffing out the X-ray producing shock zone. The companion, briefly, disappears within the primary's wind. The orbital dynamics of this binary system add an entirely new layer of complexity to an already unstable star. The gravitational interactions between the two stars may play a role in triggering or modulating eruptions. The tidal forces at periastron are significant. The wind-wind collision zone creates structures in the surrounding nebula that change shape over the course of each orbit. Astronomers have tracked these changes in detail, building three-dimensional models of the collision zone that evolve over the 5.54-year cycle, and the companion star itself may be influencing the long-term evolution of the primary in ways that are not yet fully understood. The Carinae Nebula, where this binary system resides, is itself a spectacle worth pausing over. Spanning more than 300 light-years across, it is one of the largest diffuse nebulae in the sky, a vast cloud of gas and dust illuminated by the light of hundreds of young, massive stars. It is located in the Carinae Sagittarius arm of the Milky Way, visible primarily from the southern hemisphere. On a clear night, far from city lights, it appears as a faint, glowing patch in the constellation Carinae, just bright enough to catch the eye, just faint enough to leave you wondering what it is. The James Webb Space Telescope, launched in December of 2021, captured breathtaking images of the Carinae Nebula in its early science observations in 2022. These images revealed previously unseen details of the nebula's structure, including hundreds of previously unknown young stellar objects embedded within the gas and dust, protostars in the process of forming, still swaddled in the raw material from which they are being born. JWST's infrared capabilities allowed it to peer through the dense clouds that block visible light, revealing the nurseries where new generations of stars are taking shape, even as Eta Carinae approaches its death. Consider one more comparison. If you could drive a car at highway speed, roughly 100 kilometers per hour, 24 hours a day without stopping, it would take you about 170 years to reach the Sun. That is a long drive. But it is nothing compared to the distance to Eta Carinae. At the same highway speed, reaching Eta Carinae would take roughly 81 billion years, about 6 times the current age of the universe. You could start driving at the moment of the Big Bang, drive continuously for 14 billion years, and you would have covered less than 20% of the distance. The universe itself is not old enough for such a journey at human speeds. That is how far away this star is. And yet, despite that distance, when it dies, we will see it happen with our naked eyes. That fact alone should give you pause. But Eta Carinae remains the dominant feature of this region. It sits near the center of the nebula, surrounded by the expanding debris of its own eruptions. The Homunculus Nebula, the product of the Great Eruption, stretches roughly 1 light-year from end to end. It is expanding at speeds between 300 and 600 kilometers per second. It contains somewhere between 10 and 40 solar masses of ejected material, and it is growing, day by day, year by year, pushing outward into the surrounding interstellar medium. Here is a way to think about the sheer volume of material contained in the homunculus. Take the entire mass of our Sun, rough 2 million trillion kilograms. Now multiply that by 10. That is the minimum amount of material that Eta Carinae expelled in a single event lasting roughly 20 years. It would be as though our sun simply shed 10 copies of itself and kept burning. Or picture it this way: if you could somehow gather all the water in all the oceans on Earth, and then multiply that mass by about 7 million, you would have the mass of material ejected during the Great Eruption. 7 million Earth's worth of ocean water, flung into space at hundreds of kilometers per second. That is what this star did in the span of a human generation. The energy required to accomplish this is almost beyond calculation. Conservative estimates place it at roughly 10 to the 49 to 10 to the 50 ergs, approaching the total energy output of a true supernova explosion. A supernova is one of the most energetic events in the universe. It is the death of a star, and yet the Great Eruption of Eta Carinae approached that energy level without actually killing the star. The star survived. Something is wrong with our assumptions when a star can release the supernova level energy and not die. That paradox is at the heart of everything we are about to explore, because whatever mechanism allowed Eta Carinae to survive the Great Eruption may not protect it the next time. And next time, the physics suggests, the stakes will be far higher, not just for the star, not just for the Carinae Nebula, but potentially in ways both subtle and profound for us. The story of Eta Carinae's discovery stretches back centuries, and it is a story marked by confusion, wonder, and a growing sense of unease that has only deepened with each new generation of astronomers who have turned their instruments toward this remarkable star. The star was first catalogued by the English astronomer Edmund Halley in 1677 during his expedition to the island of St. Helena in the South Atlantic Ocean. Halley, who would later become famous for predicting the return of the comet that now bears his name, was engaged in a systematic survey of the southern sky, charting stars that were invisible from European observatories. He recorded Eta Carinae as a star of the fourth magnitude, visible but unremarkable. At that time, it was simply one of many stars in the constellation Carinae, itself part of the larger, now obsolete constellation Argo Navis, the great ship of Greek mythology. There was nothing about it that suggested it would one day become one of the most studied, most debated, and most feared objects in all of astronomy. Over the following century, however, observers began to notice something unusual. The star was not constant. It brightened and dimmed in irregular patterns that defied the smooth, predictable behavior of most known variable stars. This was puzzling. Most variable stars follow regular cycles, brightening and fading over periods of days, weeks, or months. Eta Carinae followed no such pattern. Its variations were erratic, unpredictable, and sometimes dramatic. By the late 1700s, it had brightened considerably from Halley's original observation, and by the 1820s, it was among the brightest stars in the southern sky. Something was happening inside this star. Something was building. Then, in 1837, the star began a dramatic increase in brightness that would culminate in one of the most extraordinary events in the recorded history of observational astronomy. Over the next several years, Eta Carinae brightened rapidly, climbing through the magnitude scale in a way that no star had been observed to do before. By 1843, it had become the second brightest star in the entire night sky, surpassed only by Sirius, the dog star. Consider what this means. Sirius is only 8.6 light-years away. It is practically a neighbour. Eta Carinae, at 7,500 light-years, is roughly 900 times farther away. And yet, at the peak of its eruption, it appeared nearly as bright as Sirius. The sheer luminosity required for a star that distant to appear that bright to the naked eye is staggering. It means Eta Carinae was at that moment producing light at a rate that defied every existing model of stellar behavior. This was the Great Eruption. The event was observed and documented by numerous astronomers throughout the southern hemisphere. But the most detailed observations came from John Herschel, one of the most distinguished scientists of the 19th century. Herschel, the son of William Herschel, who had discovered Uranus, was conducting a comprehensive survey of the southern sky from the Cape of Good Hope in South Africa. He arrived in early 1834 and spent the next 4 years systematically cataloguing stars, nebulae, and double stars visible from southern latitudes. Herschel documented Eta Carinae's extraordinary brightness with meticulous care in his journals and letters. He noted that it rivaled Canopus, the second brightest star in the sky, and at times approached the brilliance of Sirius itself. He was, understandably, both fascinated and perplexed. Stars were not supposed to behave this way. In the astronomy of the 19th century, stars were considered fixed and unchanging, eternal points of light that maintained their brightness across the ages. The idea that a star could suddenly and dramatically increase its luminosity challenged the most fundamental assumptions of the field. The Great Eruption lasted roughly 2 decades, from the mid-1830s to the mid-1850s, though the peak brightness occurred around 1843 to 1845. During this extraordinary period, the star expelled between 10 and 40 solar masses of material, an almost incomprehensible amount of matter, forming the homunculus nebula that we observe today. The total energy released during the eruption has been estimated at approximately 10 to the 49.7 ergs. To put that in context, a typical supernova releases roughly 10 to the 51 ergs. The great eruption of Eta Carinae was within striking distance of a true supernova in terms of raw energy output. It was perhaps 1/10 or 1/100th as energetic as a full stellar explosion, depending on the model used. And yet this was not a supernova. But here's the problem. The star survived. It dimmed over the following decades, gradually fading from naked eye visibility by the early 1860s as the ejected material thickened into a dusty shroud that absorbed the visible light. But the star was still there, still burning, still massive, still fundamentally unstable. It had undergone an event of nearly supernova-level energy and had emerged on the other side, diminished but alive. No existing theory of stellar physics could fully explain how this was possible. There is a detail about the Great Eruption that is often overlooked but deeply significant. During the peak of the eruption in 1843, Eta Carinae was not just bright, it was visibly changing colour. Observers reported that the star shifted from a yellowish-white to a reddish hue over the course of months, a spectral signature consistent with a rapidly expanding photosphere, the visible surface of the star that was cooling as it grew. This is what happens when a massive shell of hot gas is ejected from a star. The shell expands, it cools. Its colour shifts from blue-white toward red as the temperature drops. The star appeared to swell and redden before the observer's eyes, a slow-motion explosion visible from thousands of light-years away. This colour change provided one of the earliest clues that the Great Eruption was not simply a brightening of the existing star, but a fundamentally different kind of event, one involving the physical ejection of material rather than a simple increase in surface temperature. The distinction is crucial. A star that brightens because its core produces more energy is doing something very different from a star that brightens because it is explosively shedding its outer layers. The latter is far more dangerous, far more energetic, and far more likely to be a precursor to complete destruction. The sailors and navigators of the 1840s who observed Eta Carinae from the decks of ships crossing the Southern Ocean had no framework for understanding what they were seeing. To them, it was simply a bright new star in the sky, a curiosity to note in their logs and perhaps to use for navigation. They could not have known that they were witnessing one of the most violent events in the recent history of our galaxy, an event whose implications would not be fully understood for another century and a half. They were, unwittingly, eyewitnesses to a cosmic catastrophe, standing at the edge of understanding without the tools to cross over. It would take the development of infrared astronomy, X-ray astronomy, spectroscopy, and computational astrophysics to begin unraveling the true nature of what those sailors had seen. And even now, nearly 2 centuries later, the mystery is not fully solved. We understand more than Herschel did, certainly. We understand more than the sailors. But the star continues to surprise us, and the complete picture remains just out of reach, like a landscape glimpsed through fog, its outlines visible but its details obscured. For more than a century after the Great Eruption, Eta Carinae remained a relatively faint object in the visible spectrum, hidden behind the ever-thickening veil of the dust and gas it had ejected. It was studied sporadically by astronomers who were aware of its dramatic history, but without the tools of modern multi-wavelength astronomy, its true nature remained elusive. People knew it was unusual. They knew it had undergone a remarkable outburst. But the physical mechanisms behind the eruption, the reason it had happened, and the reason the star had survived, were entirely mysterious. There was also a lesser eruption. In 1890, Eta Carinae brightened again, though far less dramatically than in the great eruptions of the 1840s. This secondary event expelled additional material, creating a smaller inner nebula nested within the larger homunculus, sometimes called the little homunculus. The lesser eruption confirmed that the star was not done. It was still active, still volatile, still capable of producing violent outbursts that would be considered catastrophic for any ordinary star. The fact that it erupted again, less than 50 years after the Great Eruption, suggested that whatever instability was driving the behavior was not a one-time event, but a recurring, perhaps escalating condition. The modern era of Eta Carinae research began in the mid-20th century, when the development of new observational technologies opened windows onto the electromagnetic spectrum that had previously been invisible. In the 1940s and 1950s, radio astronomy revealed that the Carinae Nebula was a powerful source of radio emission, indicating the presence of hot, ionized gas being energized by the radiation from massive stars, including Eta Carinae. In the 1960s, infrared astronomy provided the crucial breakthrough. For the first time, researchers could peer through the dust surrounding Eta Carinae and detect the radiation that the dust was absorbing and re-emitting at longer wavelengths. What they found was astonishing. Eta Carinae was one of the brightest infrared sources in the entire sky. All that visible light, all that energy that had been absorbed by the homunculus nebula was being converted and re-radiated as infrared radiation. The energy was still there. It had not diminished. It was simply hidden, obscured by a curtain of the star's own making. In 1968, the pioneering infrared astronomer Jerry Neugebauer and his colleagues at the California Institute of Technology conducted some of the first detailed infrared observations of Eta Carinae, confirming its extraordinary luminosity and establishing it as one of the most extreme objects in the galaxy. By the 1970s, it was becoming clear that this was not just an unusual star. It was something far more significant. It was a laboratory for studying the most extreme processes in stellar astrophysics, a window into a regime of mass, luminosity, and instability that few other objects could provide. The Hubble Space Telescope, deployed in 1990, transformed our understanding of Eta Carinae in ways that ground-based telescopes never could. High-resolution images taken over the following decades revealed the intricate, delicate, and deeply unsettling structure of the homunculus nebula in unprecedented detail. The twin lobes, each rough half a light-year long, were shown to have a complex internal structure, with thin walls that appear almost translucent in some wavelengths, bright equatorial skirts of material expanding outward from the star's equatorial plane, and narrow jets of material streaming from the polar regions at velocities exceeding 1,000 kilometers per second. The images were beautiful. They were also deeply troubling, because they showed unmistakably that the star was still losing mass at a prodigious rate. The eruptions had not stopped. They had only diminished. The current mass loss rate of Eta Carinae is estimated at roughly 1,000th of a solar mass per year. That might sound small. 1,000th of a solar mass is roughly the mass of Jupiter. But consider what it means when that rate is sustained over astronomical timescales. In 1,000 years, the star would lose an entire solar mass. In 10,000 years, 10 solar masses. In 100,000 years, 100 solar masses. The star cannot sustain this indefinitely. It is bleeding into space, hemorrhaging material through its powerful stellar wind, slowly and steadily losing the very mass that sustains its nuclear burning. And it gets worse. The stellar wind from Eta Carinae is not uniform. It is not a smooth, steady outflow of material like the solar wind from our sun. It is clumpy, chaotic, and highly variable, reaching speeds of up to 500 to 700 kilometers per second. The wind carries gas, dust, and ionized particles outward in all directions, but with varying density and velocity depending on latitude, longitude, and time. At the equator, the wind is denser and slower. At the poles, it is faster and thinner. This asymmetry is related to the star's rapid rotation, which deforms its shape and concentrates the radiation pressure at the poles. When this complex, structured wind collides with the wind from the companion star, Eta Carinae b, the results are violent. The companion's wind moves at roughly 3,000 kilometers per second, roughly 5 to 6 times faster than the primary's wind, but it is much less dense. When the two winds meet, the kinetic energy of the collision is converted into thermal energy, heating the gas at the shock interface to temperatures exceeding 100 million degrees. This is roughly 7 times hotter than the core of our Sun. The superheated gas emits intense X-ray radiation that has been monitored continuously by the Chandra X-ray Observatory for more than 2 decades. The X-ray monitoring has revealed a periodic pattern tied to the 5.54-year orbital cycle of the companion star. At each periastron, when the two stars are closest, the X-ray emission drops dramatically in an event known as the X-ray minimum or the spectroscopic event. This drop is steep and sudden, occurring over just a few weeks, and it lasts roughly 3 months before the X-rays recover. The leading explanation is that the primary star's dense, slow wind engulfs the companion at periastron, smothering the wind collision shock zone and extinguishing the X-ray emission. The companion, briefly, is swallowed by the primary's atmosphere. But not every X-ray minimum is the same. Careful comparison of the cycles observed in 2003.5, 2009, 2014.6, and 2020 reveals subtle but real differences in the depth, duration, and recovery of the X-ray minimum. These differences suggest that the system is evolving. The winds are changing, the mass loss rate may be fluctuating. The star is not repeating itself precisely. It is changing, cycle by cycle, orbit by orbit, in ways that may be pointing toward a larger shift. One of the deepest puzzles surrounding Eta Carinae concerns the physical mechanism behind the Great Eruption. For decades, the standard explanation was that the star had exceeded the Eddington limit. The idea was conceptually simple. The star's luminosity grew so high that radiation pressure overwhelmed gravity, and the outer layers were blown off in a catastrophic mass ejection. It was dramatic, it was elegant, and it was almost certainly incomplete. This model has intuitive appeal, but it encounters serious difficulties when confronted with the actual observations. The amount of mass ejected during the Great Eruption, estimated at 10 to 40 solar masses, is far more than standard Super Eddington wind models can easily explain. Radiation pressure alone, even at or above the Eddington limit, should not be able to unbind that much material from a star of Eta Carinae's mass. The velocities of the ejected material, some of it moving at more than 1,000 kilometers per second, are also difficult to produce with radiation alone. Something more violent, more sudden, more energetic was needed. Alternative models have been proposed, each with its own strengths and weaknesses. One of the most compelling involves a stellar merger. In this scenario, the Eta Carinae system was originally not a binary but a triple star system, with 3 massive stars orbiting one another in a complex gravitational dance. During the Great Eruption, the innermost companion spiraled inward and merged with the primary star, releasing an enormous amount of gravitational energy that powered the eruption. The merger would have deposited energy and angular momentum deep in the primary's interior, driving the catastrophic mass ejection that formed the homunculus. This merger model has several attractive features. It can naturally explain the enormous energy output. It can account for the bipolar shape of the homunculus, which would arise from the angular momentum of the merging stars. And it explains why the eruption was a singular event, not a repeating cycle, because a merger can only happen once. However, the model also has limitations. It is difficult to test directly, because any evidence of the third star would have been destroyed in the merger itself. The model also predicts certain chemical signatures in the ejected material that have been difficult to confirm observationally. Another possibility involves deep-seated instabilities in the star's nuclear burning core. Stars as massive as Eta Carinae undergo processes known as pulsational pair instabilities, in which the extreme temperatures in the core lead to the production of electron-positron pairs. These pairs reduce the internal pressure that supports the core against gravity, causing partial collapse. The core rebounds violently, sending powerful shock waves through the outer layers of the star. These pulsations can repeat multiple times, each one ejecting a shell of material, before the star either stabilizes or finally collapses entirely. A third possibility, not mutually exclusive with the others, involves the gravitational interaction between the primary star and its known companion, Eta Carinae b. At each periastron, the companion plunges through the outer atmosphere of the primary. Over many orbits, spanning thousands of years, this interaction could destabilize the primary's envelope, gradually building up to a catastrophic mass ejection event. Some models suggest that the Great Eruption was triggered by a particularly close or particularly disruptive periastron passage, one in which the companion penetrated deeper into the primary's envelope than in previous orbits. The truth may involve elements of all three scenarios. Stellar astrophysics at this extreme is not a domain of simple answers. The models are complex, the observations are limited, and the star itself seems to defy easy categorization. It refuses to fit neatly into any single theoretical framework. What is clear, however, is that the Great Eruption was not a unique event. In the broader context of massive star evolution, other massive stars have shown similar behavior, and the pattern is deeply unsettling. Objects known as supernova imposters, luminous blue variables that undergo giant eruptions without actually destroying themselves, have been observed in other galaxies. Some of these imposter events have been followed, years or decades later, by true supernovae. The star erupts, it sheds mass, it appears to stabilize, and then it explodes for real. The most recent observations of Eta Carinae reinforce the sense that the system is far from stable. Over the past 2 decades, the star has been brightening in visible light. Between roughly 1998 and 2020, its visible brightness increased by approximately a factor of 2. This brightening appears to be caused primarily by changes in the surrounding dust, which is thinning as the homunculus nebula expands and allows more of the central star's light to escape. But some astronomers have raised the possibility that the star's intrinsic luminosity may also be increasing, which would suggest that the star is entering a new phase of instability. Data from the Hubble Space Telescope, the Chandra X-ray Observatory, ground-based instruments at the European Southern Observatory in Chile, and the Gemini Observatory show a system that is complex, dynamic, and evolving. The homunculus nebula continues to expand, the stellar wind continues to blow, and the 2 stars continue their gravitational dance, approaching and retreating every 5.5 years, each encounter producing a new round of observations and a new set of questions. But here's what makes this truly terrifying. Eta Carinae is not a distant academic curiosity. It is not an object that exists only in the pages of astrophysical journals. It is a real star in our galaxy, close enough that its death will be visible to the naked eye. It is a ticking clock, and when it finally explodes, it will do so with a violence that nothing in recorded human history, nothing in the entire span of civilization, nothing since the dawn of our species, can compare to. The question is not whether it will happen. The physics guarantees that it will. The question is when. And on that question, the star keeps its silence. There is a particular kind of dread that comes from understanding probabilities without knowing outcomes. A doctor might tell you that a certain condition has a 90% survival rate. That is reassuring in its way, but it does not tell you which side of the statistic you will be on. Eta Carinae presents a similar challenge, but on a cosmic scale. We know, with high confidence, that the star will explode. We know that the explosion will be extraordinary. We know that the orientation of the system makes a direct gamma-ray burst unlikely, but not impossible. And we know that even without a gamma-ray burst, the supernova will be visible from Earth and will produce measurable effects on the interplanetary environment. What we do not know, what we cannot know from our position in time and space, is when. The uncertainty is not a failure of science. It is a reflection of the genuine complexity of the system. Eta Carinae is a binary star with a combined mass exceeding 100 solar masses, surrounded by a complex, multi-layered nebula of ejected material undergoing nuclear burning in its core at rates that change on timescales, ranging from years to minutes. Predicting the precise moment of core collapse for such an object is like predicting the exact moment a sand dune will shift in a windstorm. The physics is clear, the timing is not. Recent spectroscopic studies have added new layers to the puzzle. Analysis of emission lines from nitrogen, helium, and iron in the Homunculus Nebula has revealed chemical abundances that suggest the ejected material came from deep within the star, not just from the surface layers. This is significant because it implies that the Great Eruption was not a superficial event. It reached into the star's interior, dredging up material from layers that had already undergone nuclear processing. The nitrogen enrichment, in particular, is consistent with material that has been through the carbon-nitrogen-oxygen cycle of hydrogen fusion, material from the star's hydrogen-burning shell. If the eruption was able to reach into these deep layers, it suggests that the entire stellar structure was disrupted, not just the outermost envelope. This has implications for the star's subsequent evolution. The loss of deep layer material may have altered the internal pressure and temperature profile, potentially accelerating the star's progression toward core collapse. Some models suggest that the Great Eruption effectively aged the star by tens or hundreds of thousands of years, pushing it closer to the end of its life in a single catastrophic event. And there is the matter of the light echo. In 2003, astronomers using the U.S. National Optical Astronomy Observatory's Blanco telescope in Chile detected light echoes from the Great Eruption. Light echoes are reflections of the original light from the eruption, bouncing off distant clouds of dust and arriving at Earth with a delay of roughly 160 years. By analyzing these echoes, astronomers could study the spectrum of the eruption as it actually appeared in the 1840s, rather than relying on the limited visual observations of that era. What the light echo spectra revealed was unexpected. The Great Eruption was not a hot, radiation-driven event, as many models had predicted. Instead, the spectra showed that the ejected material was relatively cool, with temperatures of only about 5,000 degrees Celsius, roughly the temperature of the Sun's surface. This was a surprise. A super Eddington event driven by radiation pressure would be expected to produce much hotter ejecta. The cool temperatures suggested a different mechanism entirely, one more consistent with an explosive or hydrodynamic event, rather than a radiation-driven wind. This finding lent support to the merger hypothesis. A stellar merger would release gravitational energy deep within the star, driving a shock wave outward that could eject material at high velocity but relatively low temperature. The shock-heated material would expand and cool rapidly as it moved away from the star, producing exactly the kind of cool, dense ejecta observed in the light echo spectra. The light echo observations also revealed that the eruption was not symmetric. Different directions showed different spectral characteristics, indicating that the mass ejection was strongly concentrated in certain directions, particularly along the polar axis. This polar concentration is consistent with the bipolar shape of the Homunculus Nebula and suggests that whatever mechanism drove the eruption was influenced by the star's rotation or the orbital dynamics of the binary system. Additional observations in the decades since have only deepened the mystery. In 2018, a team led by astronomer Nathan Smith at the University of Arizona published a comprehensive analysis of the Homunculus Nebula using data from multiple telescopes, including Hubble and the Atacama Large Millimeter Array, known as ALMA. Their analysis revealed a complex substructure within the nebula, including filaments, clumps, and density variations that speak to the chaotic nature of the ejection process. The material is not smoothly distributed. It is lumpy and turbulent, as though it was thrown out in a series of violent pulses rather than a single smooth outflow. Smith and his colleagues also revised the mass estimate for the homunculus upward, suggesting that the total ejected mass may be closer to 40 solar masses than the earlier estimate of 10 to 15. If correct, this makes the Great Eruption even more extreme than previously thought, pushing the energy budget further towards supernova territory and making the mystery of the star's survival even more acute. The discovery of molecular gas in the homunculus added yet another dimension. ALMA observations detected molecules such as carbon monoxide, nitrogen-bearing species, and even water vapor in the expelled material. The presence of these molecules, which can only survive at relatively low temperatures, confirmed that portions of the ejecta were never heated to extreme temperatures. They were, in some sense, ripped from the star's outer layers and flung into space before the heat of the eruption could destroy them. This suggests that the eruption was not a uniform process. Some material was ejected violently, at high velocity and high temperature. Other material was stripped away more gently, carried along by the expanding shock front, but never heated to the point of molecular dissociation. The homunculus is, in effect, a layered archive of the eruption, with different regions preserving different phases and different conditions of the event. The concept of a supernova imposter has become increasingly important in modern astrophysics. These are stars that undergo eruptions so energetic that they initially appear to be supernovae, complete with dramatic brightening and the ejection of large quantities of material, but that survive the event and continue burning. Eta Carinae's great eruption is the most famous example, but it is far from the only one. In the 21st century, surveys designed to detect supernovae in distant galaxies have uncovered a growing population of these imposters. Some brighten and fade multiple times, producing a series of outbursts that span years or decades. Some show spectral signatures that evolve over time, initially resembling a supernova, but later revealing the presence of a surviving central star. And some, as in the case of SN 2009 IP, eventually transition from imposter to genuine supernova, the eruptions serving as a prologue to the final act. The growing catalogue of supernova imposters has transformed the way astronomers think about the final stages of massive star evolution. It is no longer assumed that stellar death is a single sudden event. Instead, it may be a drawn-out process, a series of increasingly violent eruptions that progressively strip the star of its outer layers before the core finally gives way. In this picture, the great eruption of the 1840s was not an anomaly. It was a step in a sequence. And the question that hangs over the field like a cloud is simple. How many more steps remain? All of this paints a picture of a star in deep trouble, a star that has already demonstrated its capacity for catastrophic mass ejection, a star that is losing mass through its stellar wind at a rate that, while less dramatic than the Great Eruption, is nonetheless unsustainable. A star that is approaching the final stages of nuclear burning in its core, and a star that, based on the behavior of analogous objects in other galaxies, may be on the verge of doing something far worse than anything it has done before. Astronomers have spent decades trying to predict when and how Eta Carinae will die. The approaches vary widely, drawing on stellar evolution theory, observational monitoring, computational simulations, comparisons with analogous objects in other galaxies, and direct risk assessment for Earth. Each approach offers genuine insights, each has significant limitations, and none, individually or collectively, provides a definitive answer. The star resists prediction as stubbornly as it resists its own gravity. The first approach is the most direct and, in some ways, the most elegant. Stellar evolution models. These are computational frameworks built on the laws of nuclear physics, thermodynamics, and gravitational mechanics that track the life cycle of a star from its birth in a collapsing cloud of gas to its death in a supernova or quiet fade. For a star like Eta Carinae, with an initial mass somewhere in the range of 100 to 150 solar masses, the models make one thing clear. The star will not die quietly. The only question is the precise manner and intensity of its death. For stars in the range of roughly 8 to 25 solar masses, the end is a Type II supernova. The core exhausts its nuclear fuel, progressing through successively heavier elements, from hydrogen to helium, carbon, neon, oxygen, and finally silicon. When silicon fusion fills the core with iron, the chain stops. Iron cannot be fused to release energy. It is the ash of the nuclear furnace. With no more fuel to burn, and no more outward pressure to support it, the core collapses in a fraction of a second. crashing inward at speeds approaching a quarter of the speed of light. The inner core compresses to form a neutron star, an object so dense that a teaspoon would weigh 1 billion tons. The rebounding shockwave, aided by a flood of neutrinos, tears through the outer layers and flings them into space. The result is a spectacular but relatively standard stellar explosion, bright enough to be visible across the galaxy, generating enough energy to briefly outshine billions of ordinary stars. For stars above roughly 25 solar masses, the picture becomes considerably more dramatic and considerably less certain. These very massive stars may collapse so completely that the shockwave fails to propagate. The entire core, and perhaps the entire star, may fall past the event horizon and form a black hole. In some models, this collapse happens silently, with no explosion at all. The star simply vanishes from the sky, leaving behind a gravitational phantom that betrays its presence only through its effect on nearby matter. In other models, the extreme conditions of the collapse produce a particularly energetic explosion known as a hypernova, potentially accompanied by a gamma-ray burst, a focused jet of high-energy radiation that can carry energy across billions of light-years. Eta Carinae, at 100 or more solar masses, sits in a regime where the models diverge significantly. Different research groups around the world, using different assumptions about convective mixing, mass loss rates, rotation, magnetic fields, and nuclear reaction networks, arrive at genuinely different conclusions about the star's fate. The range of possibilities is wide, and each possibility carries dramatically different implications. Some models predict that Eta Carinae will die in a spectacular hypernova, an explosion at the extreme end of the supernova spectrum. A hypernova can release 10 to 100 times the energy of a standard Type II supernova, producing a luminosity so great that it would be visible across intergalactic distances. If Eta Carinae undergoes a hypernova, the explosion would be visible to the naked eye in broad daylight from Earth. It would cast shadows at night. It would be, without question, the most dramatic astronomical event in recorded human history. Other models predict a pair instability supernova, a fundamentally different kind of explosion, driven not by the collapse of an iron core, but by a nuclear instability that develops at extremely high temperatures. In the pair instability scenario, the core temperature rises so high, above roughly 1 billion degrees, that the photons in the core begin to spontaneously convert into pairs of electrons and positrons. This conversion removes photon pressure from the interior, which is the very pressure supporting the star against gravitational collapse. The core contracts rapidly, and the contraction heats the oxygen and silicon so violently that they undergo thermonuclear detonation, a runaway nuclear explosion that unbinds the entire star. Nothing survives. No neutron star, no black hole. Just an expanding cloud of newly synthesized elements, enriching the interstellar medium with the heaviest products of nuclear fusion. The numbers are striking when it comes to pair instability supernovae. Such an event could release up to 10 to the 53 ergs, roughly 100 times the energy of a standard supernova. The peak luminosity could reach 10 to the 44 watts or more, making it visible across half the observable universe. If Eta Carinae were to undergo such an event at its current distance of 7,500 light-years, it would be visible in daylight for weeks, perhaps months. It would outshine the full moon at its peak, and it would leave behind nothing but an expanding shell of debris, a cosmic memorial to a star that burned too bright and too fast. Still, other models predict a different outcome entirely. If Eta Carinae has lost enough mass through its eruptions and stellar wind, its core may no longer be massive enough to trigger a full pair instability event. In this case, it might undergo a series of pulsational pair instability events instead, a sequence of partial collapses and rebounds that eject shells of material over a period of years to centuries before the star finally succumbs to a conventional core collapse. Each pulsation would be a miniature supernova in its own right, a brilliant flash of light and a wave of ejected material, building up layer after layer of debris around the dying star. But here's the problem with all of these models. They depend critically on one parameter that is poorly known: the current mass of the star. And the current mass depends on how much material the star has lost over its lifetime, through eruptions, through its stellar wind and through any merger events that may have occurred. The mass loss history of Eta Carinae is therefore the key variable, and it is one of the most poorly constrained aspects of the entire system. If the star has shed 40 or more solar masses through the Great Eruption and subsequent mass loss, its current mass may be in the range of 60 to 80 solar masses. At that mass, a pair instability supernova is unlikely. The star would instead collapse to form a black hole, possibly with a hypernova-like explosion and a gamma-ray burst. If the mass is higher, closer to 100 solar masses, a pair instability event becomes possible. The difference between these outcomes is the difference between the most spectacular explosion in human history and a relatively quiet disappearance behind an event horizon. And the difference depends on a number, the current mass, that no one can measure directly. The second approach involves direct observational monitoring, and it is where the day-to-day work of understanding Eta Carinae takes place. Astronomers have been watching this star intensively, with increasing sophistication, for more than 2 decades. The goal is not just to study the star as it is now, but to detect changes that might signal an approaching catastrophe. The Hubble Space Telescope has been a cornerstone of this effort. Its high-resolution imaging capabilities, unmatched by any ground-based telescope at visible wavelengths, allow astronomers to track the expansion of the Homunculus Nebula with extraordinary precision, measuring changes in position as small as a few milliarcseconds per year. Hubble has also been used to monitor the star's brightness across the visible spectrum, to study the emission and absorption lines in its spectrum, and to image the wind-wind collision zone between the two stars. Key findings from the Hubble monitoring program include the detection of a steady increase in visible brightness since the late 1990s. This brightening was initially puzzling because the star's intrinsic luminosity did not appear to be changing. The explanation turned out to be that the Homunculus Nebula, the dusty shroud surrounding the star, was thinning as it expanded, allowing more of the central star's light to escape. In essence, the curtain was being drawn back, revealing a star that had been there all along, burning with undiminished fury behind its self-made veil. But more recent data have complicated this picture. Some analyses suggest that the brightening may not be entirely due to thinning dust. There are indications that the star's mass loss rate has decreased over the past 2 decades, which would reduce the density of the surrounding wind and allow more light to escape. A reduction in mass loss rate could have several explanations. It could indicate that the star is transitioning to a new evolutionary phase. It could mean that the instability that drove the Great Eruption is subsiding, at least temporarily. Or it could be a prelude to a new eruption, a brief calm before the next storm. The Chandra X-ray Observatory has provided an independent and complementary monitoring dataset. By observing the X-ray emission from the wind-wind collision zone, Chandra tracks the binary orbit in real time, recording each periastron passage and comparing it with previous cycles. The X-ray light curve, the graph of X-ray brightness over time, has become one of the most important diagnostic tools for studying the system. It reveals not just the orbital period but the physical conditions in the collision zone, the density and velocity of the winds, the geometry of the shock front, and any changes in these parameters from one orbit to the next. The monitoring results have shown that the X-ray emission is slowly increasing over time, cycle by cycle. The peaks are getting higher. The recovery from each X-ray minimum is slightly faster. These trends are consistent with a gradual decrease in the mass loss rate of the primary star, which would allow the companion's faster wind to penetrate deeper and create a stronger shock. This interpretation is consistent with the visible brightening observed by Hubble, and it points to a system that is evolving, even on timescales as short as decades. Ground-based observatories have also contributed essential data. The European Southern Observatory's Very Large Telescope in Paranal, Chile, equipped with adaptive optics systems that compensate for atmospheric turbulence, has obtained some of the highest resolution images of the inner regions of the Eta Carinae system ever achieved from the ground. These observations have revealed the complex structure of the wind collision zone and the inner nebula with a level of detail that complements, and in some cases, surpasses what Hubble can achieve. The Gemini South Telescope, also in Chile, has been used for infrared spectroscopy, probing the chemical composition and physical conditions of the ejected material, and a global network of smaller telescopes spanning multiple continents and operated by collaborations of professional and amateur astronomers has provided continuous monitoring of the star's brightness at visible wavelengths, filling in the gaps between observations from the larger facilities. The limitation of observational monitoring, however, is fundamental. It tells us what the star is doing now. It does not tell us what the star will do in the future. Stellar evolution occurs on timescales of thousands to millions of years. A human lifetime, or even a few centuries of dedicated observation, represents an infinitesimally small snapshot in the life of a star. We are watching a process that has been unfolding for 3 million years, and we have been observing it seriously for perhaps 200. It is like watching a single frame of a movie that lasts 10,000 hours and trying to predict the ending from that one frozen image. Nevertheless, the observations have yielded important clues. The increasing brightness, the changing spectral characteristics, the cycle-to-cycle variations in X-ray behavior, all of these suggest that the system is not in a steady state. It is changing. It is evolving. Whether those changes are pointing toward an imminent eruption, a supernova, or simply a new phase of variability is an open question. But the evidence strongly suggests that Eta Carinae today is not the same object it was 50 years ago, and it will not be the same object 50 years from now. The third approach involves studying analogous objects, stars in other galaxies, that share some of Eta Carinae's extreme characteristics, and whose behavior might offer clues about what lies ahead. Eta Carinae is not the only massive unstable star known to science. Across the observable universe, astronomers have identified dozens of luminous blue variables, massive stars that undergo dramatic changes in brightness and mass loss. These objects occupy the same extreme corner of the Hertzsprung-Russell diagram, the fundamental chart that maps stars by their temperature and luminosity. And some of them have been caught in the act of erupting, providing real-time data on the physics of giant eruptions that can be compared with Eta Carinae's historical behavior. One of the most important and most disturbing analogues was an object designated SN 2009 IP, observed in the spiral galaxy NGC 7259, roughly 73 million light-years away. This object was first detected as a luminous transient, a sudden brightening that appeared to be a supernova. But follow-up observations revealed that it was not a single explosion. It was a series of outbursts, eruptions of increasing intensity that occurred over several years. The pre-explosion outbursts were strikingly similar to Eta Carinae's Great Eruption, involving massive ejections of material at high velocities, creating expanding shells and lobes of gas around the star. Then, in late 2012, the outbursts stopped, and the star exploded for real. The true supernova was several times more luminous than the earlier outbursts, and displayed the spectroscopic signatures of a genuine core collapse event. The pre-explosion eruptions had been, in retrospect, the death throes of the star, a series of increasingly desperate attempts to shed mass before the final collapse. The discovery of SN 2009 IP sent a shockwave through the community of astronomers studying Eta Carinae. The parallels were too close to ignore. A massive star undergoing giant eruptions, shedding enormous quantities of mass, producing a bipolar nebula, and then, after decades of instability, finally exploding as a supernova. It was, in miniature, the story that many feared Eta Carinae would eventually tell. Another important analogue is SN 2006 GI, one of the most luminous supernovae ever observed. This explosion, detected in a galaxy roughly 240 million light-years away, released approximately 100 times the energy of a typical Type II supernova. Some models suggest it was a pair instability supernova, the very type of explosion that certain theoretical models predict for Eta Carinae. Other models interpret it as the collision of a supernova shockwave with a dense shell of previously ejected material, a model that could apply to Eta Carinae if it explodes while surrounded by the homunculus nebula. There is also the case of P Cygni, a luminous blue variable in our own Milky Way that underwent a major eruption in the 1600s. P Cygni brightened dramatically in 1600 and the years following, becoming visible to the naked eye before fading again over the following decades. The star survived its eruption and remains visible today, having settled into a relatively stable state. P Cygni is often cited as an analogue for Eta Carinae, but it is an imperfect one. P Cygni is less massive, probably around 30 to 50 solar masses, and less luminous. Its eruption, while dramatic, was far less energetic than Eta Carinae's great eruption. It is perhaps a cousin rather than a twin, and there is AG Carinae, another luminous blue variable in the Milky Way, surrounded by a ring nebula of ejected material. AG Carinae has been observed to undergo brightness variations of more than a magnitude over timescales of years, with associated changes in its spectral type. It is less extreme than Eta Carinae, but it demonstrates that the luminous blue variable phenomenon, with its cycles of eruption and relative quiescence, is not unique to a single object. The limitation of the analog approach is obvious but worth stating explicitly. Every massive star is different. They have different masses, different chemical compositions, different rotation rates, different binary companions, or lack thereof, different magnetic field strengths, and different evolutionary histories. What happens to one may not happen to another. The analogues provide context, inspiration, and cautionary tales, but they do not provide certainty. Eta Carinae will tell its own story in its own time. The fourth approach is computational simulation, and it is here that the cutting edge of theoretical astrophysics meets the limits of what even the most powerful computers can achieve. Modern supercomputers can simulate the interior of a massive star in 3 dimensions, tracking the turbulent flow of energy through convective cells, the progress of nuclear reactions in the core, the behavior of neutrinos as they stream outward, and the dynamics of mass ejection during eruptions and explosions. These simulations are enormously complex, requiring months of computer time on some of the world's largest machines. One of the leading research groups in this field has been based at the University of California, Santa Cruz, led by the astrophysicist Stan Worsley. Over the course of several decades, Worsley and his collaborators have produced some of the most detailed and widely cited models of massive star evolution and death. Their simulations explore how stars in the range of 100 to 300 solar masses navigate the treacherous final stages of their lives, encountering pair instabilities, pulsational instabilities, and ultimately core collapse. Their results paint a landscape of possibilities that is both fascinating and deeply uncertain. Depending on the exact mass, metallicity, and rotation rate of the star at the end of its life, the outcome can range from a quiet collapse to a black hole, through a standard supernova to a full pair instability supernova that obliterates the star entirely. The transitions between these outcomes are sharp. A change of just 5 or 10 solar masses in the final core mass can shift the star from one fate to another. And since the final core mass depends on the entire history of mass loss over the star's lifetime, a quantity known with limited precision, the predictions carry large uncertainties. For Eta Carinae specifically, the simulation suggests the following general picture. If the star's current mass is above roughly 90 to 100 solar masses, a pair instability event is possible, though not certain. If the mass is between roughly 40 and 90 solar masses, the most likely outcome is core collapse to a black hole, possibly accompanied by a hypernova and a gamma-ray burst. If the mass has dropped below roughly 40 solar masses through extensive mass loss, a more conventional Type II supernova is expected, though even this would be extraordinary given the star's history. Recent 3-dimensional simulations by multiple groups have also explored the role of the binary companion in shaping the system's evolution. Hydrodynamic models of the wind-wind collision zone, run on high-performance computing clusters, have reproduced many of the observed features of the X-ray emission, including the periodic minimum at periastron and the asymmetric structures in the surrounding nebula. These simulations have shown that the companion's influence on the primary's outer layers is significant and complex, creating density variations, shock structures, and turbulent mixing regions that evolve over each orbital cycle. Some of the most provocative computational work has explored the merger hypothesis for the Great Eruption, three-dimensional smooth particle hydrodynamic simulations of a stellar merger, in which a lower mass companion spirals into and merges with a massive primary star, have been able to reproduce several key features of the observed homunculus nebula, including its bipolar shape, its expansion velocity, and its total mass. These simulations suggest that a merger event could naturally produce the kind of energetic, asymmetric mass ejection that created the homunculus without requiring the star to exceed the Eddington limit. If the merger hypothesis is correct, it has profound implications for the star's future. The merger would have deposited a significant amount of angular momentum and thermal energy deep in the primary's interior, fundamentally altering its internal structure and its subsequent evolutionary trajectory. A star that has swallowed a companion is not the same as a star that has evolved in isolation. Its core may be hotter, its convective patterns may be different, and its progression toward core collapse may be accelerated or delayed in ways that are difficult to predict without more sophisticated models. The fifth approach is perhaps the most consequential from a human perspective. It involves assessing the risk that Eta Carinae's death could pose to life on Earth. The primary concern is gamma-ray bursts. When certain types of massive stars collapse, they can produce narrow, highly collimated beams of gamma radiation along their rotational axes. These jets can carry an enormous fraction of the total explosion energy in a concentrated beam that sweeps across space like a cosmic lighthouse. A gamma-ray burst directed at Earth from a distance of 7,500 light-years could, depending on its energy and duration, deplete the ozone layer by 30 to 50%, dramatically increasing the flux of ultraviolet radiation reaching the surface. The immediate effects on life would be subtle but cumulative. Increased ultraviolet radiation would damage the DNA of surface-dwelling organisms, increase rates of skin cancer and cataracts in animals, and suppress photosynthesis in plants and marine algae. The most vulnerable organisms would be the phytoplankton in the upper layers of the ocean, microscopic photosynthetic organisms that form the base of the marine food chain. A significant reduction in phytoplankton populations could cascade through the entire ocean ecosystem, affecting fish, marine mammals, and ultimately the human food supply. The good news, and it is genuinely good news, is that Eta Carinae's rotational axis does not appear to be aimed at Earth. The bipolar lobes of the homunculus nebula indicate the orientation of the system's spin axis, and they point roughly 40 to 50 degrees away from our line of sight. If the gamma-ray burst follows this axis, the main beam would miss Earth by a comfortable margin. But this reassurance comes with several important caveats. The rotational axis of the star could shift during the final stages of core collapse, particularly if the collapse is asymmetric, which is typical. The jet produced by a gamma-ray burst is not perfectly narrow. It has some angular spread, and even the off-axis emission from a powerful burst at close range could be significant. And there are secondary effects beyond the main jet, including a burst of cosmic rays, energetic charged particles, that would arrive at Earth over a period of centuries to millennia, potentially driving further ozone depletion and climate effects. Even without any gamma-ray burst, the supernova itself would be a remarkable event as observed from Earth. At 7,500 light-years, a standard core collapse supernova would appear as a point of light roughly -7 to -8 in apparent magnitude, several times brighter than Venus, and easily visible in daylight. It would be the brightest stellar explosion observed from Earth since the supernova of 1054, which was recorded by Chinese and possibly Islamic astronomers as a guest star visible in daylight for 23 days. A hypernova from Eta Carinae could be several magnitudes brighter still, rivaling the quarter moon in apparent brightness. The optical display would evolve over weeks and months. Initially, the star would brighten rapidly over a period of hours as the shock wave reached the surface. It would then reach peak brightness and plateau for days to weeks, depending on the type of explosion. After the peak, it would begin a slow decline, fading over months as the expanding debris cooled and became transparent. The supernova remnant, an expanding shell of hot gas and energetic particles, would remain visible to telescopes for thousands of years. The expanding debris from the supernova would interact with the homunculus nebula, sweeping up the material from the great eruption and accelerating it to even higher velocities. This interaction could produce intense radiation across the electromagnetic spectrum, from radio waves to gamma rays, as the shock wave plowed through the dense shells of previously ejected material. The collision between the supernova ejector and the homunculus could in fact make the event more luminous than it would be if the star exploded in a clean, unobstructed environment. The supernova remnant itself would continue expanding for hundreds of thousands of years, eventually reaching a diameter of many light years. The material enriched with heavy elements, the oxygen and carbon and silicon and iron forged in Eta Carinae's core, and during the explosion, would mix with the surrounding interstellar medium, contributing to the raw material from which future generations of stars and planets will form. At its current distance, the expanding debris from the supernova would reach the outer boundary of our solar system in roughly 400,000 years. By that time, the material would have slowed considerably and would pose no direct physical threat to Earth. The radiation from the explosion, traveling at the speed of light, would arrive long before the debris, and it is the radiation, not the debris, that would have the most immediate effects. Each of these 5 approaches, stellar evolution models, observational monitoring, analogues, computational simulations, and risk assessment, contributes an essential piece to the puzzle of Eta Carinae. But none provides a complete picture. The star remains enigmatic, resistant to easy classification, stubbornly unpredictable. Its behavior continues to surprise even the most experienced researchers, and its future remains balanced on a razor's edge between several possible fates, each with dramatically different implications. There is a particular challenge in modeling the final stages of Eta Carinae's evolution that deserves specific mention. It involves the interaction between the supernova ejector and the pre-existing circumstellar material, the homunculus nebula, and the stellar wind that surrounds the star. When a supernova shockwave slams into a dense shell of previously ejected material, the kinetic energy of the collision is converted into radiation with extraordinary efficiency. The result can be a supernova that is far more luminous than it would be in the absence of the circumstellar material. This phenomenon is known as a type Ia supernova, where the lowercase n stands for narrow emission lines in the spectrum, produced by the shock-heated circumstellar gas. Several of the most luminous supernovae ever observed have been type Ia events, and some astronomers believe that Eta Carinae, if it explodes while still embedded in the homunculus, could produce one of the most luminous supernovae in history, not just because of the energy of the explosion itself, but because of the tremendous amount of energy that would be released when the blast wave plows through the dense, massive, expanding shell of material from the Great Eruption. The mass of the homunculus, estimated at 10 to 40 solar masses, is enormous by the standards of circumstellar nebulae. A standard type Ia supernova interacts with perhaps a solar mass or less of circumstellar material. Eta Carinae would be interacting with 10 to 40 times that amount. The resulting display could be extraordinary, potentially rivaling or exceeding even the intrinsic luminosity of the supernova itself. The homunculus, which has served as a shroud hiding the star from view for over a century, could become, in the event of a supernova, a luminous amplifier, converting the kinetic energy of the blast into visible light with devastating efficiency. This scenario has been modeled by several research groups, and the results are consistently dramatic. Peak luminosities of 10 to the 43 to 10 to the 44 watts are plausible, making the event visible across cosmological distances. From Earth, at 7,500 light-years, the supernova could rival the brightness of the full moon for days or weeks. The afterglow from the shock interaction could persist for years, as the blast wave progressively encounters different density structures within the homunculus. It is worth acknowledging a point that is sometimes lost in the drama of discussions about Eta Carinae. The timescale for the star's death, while geologically short, may still be long by human standards. When astronomers say that Eta Carinae could explode soon, they are speaking in cosmic terms. Soon could mean tomorrow. It could also mean 50,000 years from now. Both of these timescales are vanishingly short in the context of a star's 3 million-year life. But they are very different from a human perspective. 50,000 years ago, our ancestors were painting caves in what is now France and Spain. The entire history of agriculture, cities, writing, science and technology fits within the last 10,000 years. Even the most conservative estimates for Eta Carinae's remaining lifetime place the event within a timescale that overlaps, at least in the broadest sense, with the timescale of human civilization. Some researchers have attempted to narrow the window by looking for specific observational signatures that might indicate how close the star is to core collapse. Changes in the neutrino emission from the core, for instance, could in principle signal the onset of the final nuclear burning stages. But neutrinos from a star 7,500 light-years away are far too faint to detect with current technology unless the star is actively collapsing. We would need a detector millions of times more sensitive than IceCube to pick up the steady-state neutrino emission from Eta Carinae's burning core. For now, that capability does not exist. Other researchers have looked for changes in the star's surface properties that might reflect changes in the core. In theory, as the core contracts and heats up during the final burning stages, the effects should propagate outward through the star, altering the surface temperature, luminosity, and pulsation behavior. But these signals are difficult to distinguish from the much larger variability caused by the stellar wind, the binary orbit, and the ongoing mass loss. The signal is there perhaps, but it is buried in noise. What is clear across all 5 approaches is that Eta Carinae will not fade gently into the cosmic background. It will go out with violence. Spectacular, terrifying, awe-inspiring violence. The only open questions are the magnitude of that violence, its precise timing, and the extent of its consequences for the galaxy and for us. And for those questions, the best answer science can offer is an honest and humbling admission. We do not yet know, but we are watching. Every day, with every instrument we can bring to bear, we are watching. There is a deeper reality to Eta Carinae that goes beyond the physics and the predictions, beyond the models and the monitoring programs, beyond the technical language of astrophysics and the careful hedging of scientific papers. It is the reality of what this star represents in the broader context of cosmic evolution, in the vast, slow, relentless process by which the universe builds complexity out of simplicity, life out of lifelessness, consciousness out of chaos. Every atom of carbon in your body was made in a star. This is not a metaphor. It is not a poetic embellishment. It is a statement of physical fact. The carbon atoms in your DNA, in the proteins of your muscles, in the fats that insulate your nerves, every single one of them was forged in the nuclear furnace of a stellar core, at temperatures of hundreds of millions of degrees, under pressures that would crush any material on Earth into nothingness. Every atom of oxygen you breathe was created in the same way, fused from carbon and helium in the deep interior of a massive star and then scattered across space when that star died. The iron in your blood, roughly 3 to 4 grams of it circulating through your body at this very moment, was synthesized in the final seconds of a massive star's life in the furious cascade of nuclear reactions that occurs just before core collapse. The calcium in your bones was made in supernova explosions. The phosphorus in your DNA, the sulfur in your proteins, the zinc and copper and manganese that serve as catalysts in your biochemistry, all of it was created in stars and distributed through the cosmos by their deaths. You are, in the most literal sense possible, made of star stuff. The atoms in your left hand may have come from a different star than the atoms in your right hand. Your body is an assembly of materials gathered from across the galaxy, temporarily organized into a pattern complex enough to think and feel and wonder about its own origins. Eta Carinae, when it finally explodes, will seed the surrounding interstellar medium with a staggering abundance of these heavy elements. The nucleosynthesis occurring in its core right now, the slow, steady fusion of progressively heavier elements, one into the next, is building the raw materials for future solar systems, future planets, future oceans, perhaps future life. The silicon being fused into iron in the star's innermost regions will one day be the silicon in the rocks of an alien world. The oxygen being generated in the shell above will one day be the oxygen in an alien atmosphere. The carbon will one day be the carbon in molecules that might, under the right conditions, become the building blocks of biology. Let that sink in. The star that may produce the most violent explosion in our galactic neighborhood during the span of human civilization is also a factory for the elements that make biology possible. Its death will be destructive on scales that strain the imagination. The shockwave will tear through surrounding gas clouds. The radiation will sterilize nearby planetary systems. Any world orbiting a star within a few dozen light-years of Eta Carinae will be, at best, severely altered. At worst, it will be rendered lifeless. The destruction is real and it is significant, but it will also be creative. From the expanding remnant of its explosion, from the enriched gas that mixes with the surrounding interstellar medium, new stars will form. Around those new stars, new planets will coalesce out of the dust and debris. And on some of those planets, under the right conditions, with the right chemistry and the right amount of time, the atoms forged in Eta Carinae's core might arrange themselves into molecules. Those molecules might arrange themselves into cells. Those cells might arrange themselves into organisms. And those organisms might, one day, look up at their sky and wonder where they came from. This is the cycle. Stars are born from collapsing clouds of gas and dust. They burn for millions or billions of years, fusing light elements into heavy ones. They die, scattering those heavy elements across space. And from the enriched debris, new stars are born, richer in heavy elements than their predecessors, capable of forming rocky planets and complex chemistry that the first generation of stars could never have produced. Each generation builds on the last. Each death enables new creation. This is not science fiction. This is the observed, documented, verified reality of how the universe works. It has been confirmed by decades of observations, spectroscopic analyses, and computational models. It is one of the most profound discoveries in the history of science. And Eta Carinae is one of the most dramatic examples of this process in action. Consider the timeline, because timelines reveal truths that individual facts cannot. Eta Carinae formed roughly 3 million years ago, condensing from a cloud of gas and dust in the Carinae Nebula. The cloud itself was enriched by the deaths of earlier generations of stars. Stars that had burned and died billions of years before. Eta Carinae inherited their legacy, their heavy elements, their chemical complexity. At the same time that Eta Carinae was forming, roughly 3 million years ago, on a small rocky planet orbiting an unremarkable yellow star 26,000 light-years away, our distant ancestors were taking their first tentative steps on the plains of East Africa. Australopithecus afarensis, a small bipedal primate with a brain roughly 1/3 the size of a modern human's, was learning to walk upright, to use simple tools, to navigate a world of predators and scarcity. The entire arc of human evolution, from those first hominids to the civilization that now spans the globe, has unfolded within the lifespan of this single star. Every empire that has risen and fallen, every language that has been spoken and forgotten, every war that has been fought, and every peace that has been made, all of it has occurred while Eta Carinae has been burning through its nuclear fuel. While we were inventing agriculture and building cities and splitting atoms and landing on the moon, this star has been steadily converting hydrogen into helium, helium into carbon, carbon into heavier and heavier elements, progressing inexorably toward the iron core that will be its undoing. The progression through nuclear burning stages is one of the most elegant and terrifying sequences in all of astrophysics, and it is worth pausing to understand in some detail. It begins with hydrogen fusion, the same process that powers our sun. In Eta Carinae, hydrogen fusion in the core lasted roughly 2 to 3 million years. That is the longest phase, the stable burning that sustained the star through most of its life. When the hydrogen in the core was exhausted, gravity compressed the core further, raising the temperature until helium fusion ignited. Helium burning lasts a few 100,000 years. When the helium was used up, the cycle repeated. Carbon fusion ignited. Carbon burning might last a few thousand years, then neon, then oxygen, then silicon. Each stage is shorter than the last, dramatically shorter. If hydrogen burning is a marathon, helium burning is a sprint. Carbon burning is a dash. and silicon burning, the final stage, is over in a matter of days, perhaps as few as 1 or 2 days. After millions of years of steady burning, the star's final act plays out in less time than it takes the Earth to complete a single rotation. When silicon fusion fills the core with iron, the end is immediate. Iron is the most tightly bound nucleus. Fusing iron does not release energy, it absorbs it. The core, suddenly robbed of its energy source, can no longer support itself against gravity. It collapses. The collapse takes less than a second. The inner core, containing roughly 1.5 solar masses of iron, compresses from a sphere the size of the Earth to a sphere roughly 20 kilometers across. The density reaches hundreds of trillions of grams per cubic centimeter. A teaspoon of the core material would weigh roughly 1 billion tons on Earth's surface. The temperature soars past 100 billion degrees. What happens next depends on the mass. If a neutron star forms, the collapse rebounds. The infalling outer layers of the core bounce off the incredibly dense, incompressible surface of the neutron star. A shockwave races outward. Neutrinos, those ghostly particles that pass through matter almost without interacting, flood outward from the core in such enormous numbers that despite their weak interactions, they deposit enough energy in the infalling material to revive the stalled shockwave. The star tears itself apart from the inside. If a black hole forms instead, the collapse may not rebound. The entire core may pass through its own Schwarzschild radius and vanish behind an event horizon, a boundary in spacetime from which nothing, not matter, not light, not information, can escape. In some models, the outer layers of the star still explode outward, driven by the tremendous energy released during the collapse. In other models, the star simply falls in on itself, swallowed by a gravitational pit of its own making. A star that shone for 3 million years, gone in a heartbeat. For Eta Carinae, with its extreme mass and its complex binary dynamics, the core collapse, when it comes, will be extraordinarily violent regardless of the specific outcome. If it produces a hypernova, the explosion could release more energy in a few seconds than our Sun will produce in its entire 10 billion year lifespan. The shockwave would propagate outward through the homunculus nebula at a fraction of the speed of light, sweeping up the ejected material from the great eruption and the lesser eruption and all the years of stellar wind, compressing it, heating it, accelerating it. The resulting supernova remnant would be one of the largest, most energetic, and most complex structures in the galaxy. Let that sink in. A single star dying in a few seconds, producing more energy than our Sun will produce in 10 billion years. A single event lasting less time than it takes to draw a breath, releasing more energy than 100 billion years of sunlight. These numbers are not exaggerations. They are the sober, calculated predictions of physics, verified by observations of supernovae in other galaxies. They are real, and we might see it happen, not in some distant geological epoch, not in the far future when our species has evolved beyond recognition. We might see it happen in our lifetime, or in our children's lifetime, or in 100 generations. The uncertainty is genuine, and it is important. The star could explode tomorrow. It could burn for another 50,000 years. But the weight of evidence suggests that Eta Carinae is in the final stages of its existence. The instabilities, the eruptions, the mass loss, the chemical evidence of advanced nuclear burning, all of these point toward a star that is approaching the end of the road. The historical record reinforces this assessment. The Great Eruption of the 1840s was not a supernova, but it may have been a precursor to one. The phenomenon of pre-supernova eruptions has been observed in multiple cases in other galaxies. The implication is sobering. The Great Eruption was not the main event, it was the overture, it was the warning. There is one final dimension to this story that adds a layer of existential vertigo. The light we see from Eta Carinae left the star roughly 7,500 years ago. The star we observe is not the star as it exists at this moment. It is the star as it was when the first cities were being built in Mesopotamia, when the pyramids of Egypt were still centuries in the future. The star that exists right now at this instant is 7,500 years further along in its evolution. It may have already exploded. The light from that explosion may already be traveling toward us, and we would have no way of knowing. This is the peculiar and profound reality of observational astronomy. We can never see the present, we can only see the past. The deeper we look into space, the further back in time we are looking. And for an object like Eta Carinae, the gap between what we observe and what actually exists is 7,500 years wide. Civilizations have risen and fallen in that time. The entire written history of humanity fits within that gap. The star we study and the star that exists may be two entirely different things. If Eta Carinae has already exploded, the first warning we would receive would be a flood of neutrinos arriving at Earth roughly 3 hours before the visible light. Neutrino detectors, facilities like IceCube at the South Pole, Super Kamiokande in Japan, and the planned Hyper Kamiokande would register a burst of neutrinos so intense and so unmistakable that it would trigger immediate alerts to astronomical observatories around the world. Within hours of the neutrino alert, the first photons would arrive. A new star would appear in the constellation Carinae, brighter than anything seen in the southern sky in centuries. Within days, it would be visible in daylight, and the world would watch, in wonder and in fear, as the death of a star unfolded in real time. There is a phenomenon known as a neutrino burst that would serve as the first herald of Eta Carinae's death, and it is worth understanding what this would mean in practical terms. When the core of a massive star collapses, the vast majority of the gravitational energy released, roughly 99% of it, is carried away by neutrinos. These particles interact so weakly with ordinary matter that they pass through the entire star in a fraction of a second, emerging before the shockwave has even begun to propagate through the outer layers. For a supernova at 7,500 light-years, the neutrino flux at Earth would be enormous. The IceCube Neutrino Observatory, a detector consisting of over 5,000 optical sensors embedded in a cubic kilometre of Antarctic ice, would register tens of thousands of neutrino interactions within a span of roughly 10 seconds. Super Kamiokande in Japan, a tank containing 50,000 tons of ultra-pure water deep beneath the Japanese Alps, would detect thousands more. Even smaller detectors around the world would see a clear, unmistakable signal. The neutrino burst would arrive at Earth approximately 3 hours before the first photons. Because the photons are trapped inside the collapsing star, bouncing from atom to atom, slowly diffusing outward, while the neutrinos stream through the stellar material as though it were not there. Those 3 hours would be a window of extraordinary anticipation. The scientific community would know, with certainty, that a supernova had occurred. They would know the approximate direction. They would know the approximate distance, based on the neutrino count. And they would know that within hours, a new light would appear in the sky. A light that has not been seen in 400 years. The mobilization of telescopes during those 3 hours would be unlike anything in the history of astronomy. Every major observatory on Earth, every satellite in orbit capable of observing in any wavelength, every amateur astronomer with a clear view of the southern sky, would be alerted and aimed at the constellation Carinae, waiting for the first glimmer of visible light from the explosion. The data collected during the first minutes and hours of the event would revolutionize our understanding of supernova physics, providing direct observations of a nearby core collapse event with a precision and coverage never before achieved. The philosophical weight of Eta Carinae becomes even heavier when you consider what it tells us about the nature of beauty and destruction in the universe. The Homunculus Nebula is, by any aesthetic standard, one of the most beautiful objects in the sky. Its symmetrical, hourglass shape, illuminated from within by one of the most luminous stars in the galaxy, has been compared to a butterfly, a figure 8, and even an angel. Astronomers have devoted careers to studying its structure, and images of it have appeared in museums, textbooks, and magazines around the world. But this beautiful object is a wound. It is the scar left by a catastrophic eruption that nearly destroyed the star. It is made of stellar material ripped from the star's body by forces that pushed it to the edge of existence. Every filament, every wisp, every glowing tendril of gas in the homunculus represents mass that the star can never recover, fuel that it can never burn, weight that will never again contribute to the gravitational pressure holding the core together. The beauty of the nebula and the violence that created it are inseparable. One cannot exist without the other. This duality, beauty born from violence, is not unique to Eta Carinae. It is a fundamental feature of the universe. The most beautiful nebulae in the sky, the Crab Nebula, the Veil Nebula, the Cassiopeia supernova remnant, are all the remnants of stellar death. The rings of Saturn, among the most visually stunning objects in the solar system, may be the debris of a destroyed moon. The Grand Canyon, one of the most breathtaking natural landscapes on Earth, was carved by the slow, relentless destruction of rock by water. Beauty and destruction are not opposites, they are partners. We live in a universe that is simultaneously beautiful and violent, creative and destructive, nurturing and utterly indifferent to our existence. Eta Carinae embodies all of these contradictions in a single point of light. It is a star that creates the elements of life while threatening to annihilate everything around it. It is an object of breathtaking structural beauty. The Homunculus Nebula is one of the most visually stunning objects in all of astronomy that exists in a state of perpetual crisis. It is a reminder that the cosmos does not consult our schedules, does not accommodate our plans, and does not care about our survival. It simply operates according to the laws of physics, producing consequences that we must observe, measure, and attempt to understand. And somewhere in the southern sky, shining with a light that left it before the invention of writing, it waits. What does it mean for a species like ours to live in a universe that contains objects like Eta Carinae? It is a question that sits at the intersection of science and philosophy, at the boundary between what we can measure and what we can only feel. And it does not have a simple answer. Perhaps it does not have an answer at all. Perhaps the question itself is the point. We are a species that evolved on a small rocky planet, orbiting an average star in an unremarkable corner of the galaxy. Our entire civilization, every city ever built, every language ever spoken, every piece of music ever composed, every equation ever written on a blackboard, has unfolded within a thin biosphere clinging to the surface of a world that is, in cosmic terms, vanishingly small. If the Milky Way were the size of the continental United States, our entire solar system would be smaller than a grain of sand. And we, the beings who have named the stars and measured the distances between them, are smaller still. Microscopic, invisible, statistically insignificant in the ledger of cosmic accounting. And yet, from this microscopic vantage point, this mote of dust suspended in a sunbeam, we have managed to detect, observe, and partially understand a star 7,500 light-years away that is tearing itself apart. We know its mass to within a factor of 2. We know its luminosity to within a factor of 3. We know the period of its binary orbit to within a few days. We know the temperature of the gas in its wind collision zone to within a few million degrees. We have mapped the three-dimensional structure of the nebula it created, traced the chemical composition of its ejector, monitored its X-ray emission cycle by cycle, and predicted, in broad strokes, the manner and approximate timing of its death. This is a remarkable achievement. It is, in some ways, the most remarkable thing our species has ever done. Not the landing on the moon, not the splitting of the atom, not the sequencing of the genome, though all of those are extraordinary in their own right. The most remarkable thing is the sheer audacity of the attempt, that a species of primates, evolved to gather fruit and avoid predators on a tropical savanna, has taught itself to read the biography of a star 7,500 light-years away, a star it cannot touch, cannot visit, cannot influence in any way, simply by collecting the photons that happen to fall on this small patch of space at this particular moment in time. That is extraordinary, but it is also humbling, because for all our knowledge, all our instruments, all our mathematical sophistication, we cannot predict when the explosion will occur with any precision. We cannot prevent it. We cannot redirect it. We cannot shield ourselves from its consequences if the geometry turns out to be unfavorable. We are spectators, sitting in the gallery of the cosmos, watching a performance that will unfold on its own terms, according to its own script, indifferent to our presence in the audience. There is a philosophical tradition that finds meaning in precisely this kind of helplessness. The ancient Stoics, writing in the centuries before and after the Common Era, spoke of the importance of distinguishing between what is within our power and what is not. The orbit of Eta Carinae is not within our power. The nuclear reactions in its core are not within our power. The timing of its death is not within our power. What is within our power is how we respond to the knowledge of these things. Whether we respond with fear, with curiosity, with awe, with resignation, or with some combination of all of these, that is ours to decide. The Buddhist concept of impermanence offers a complementary perspective. All phenomena are transient. All structures are temporary. All forms arise, persist for a time, and then dissolve. Stars are born, stars die, galaxies merge, galaxies dissipate. Even the protons that make up the atoms in our bodies may eventually decay, given enough time, leaving nothing but a thin soup of photons and neutrinos in an ever-expanding, ever-cooling universe. Impermanence is not a tragedy, it is a description of reality. And reality, when properly understood, does not require our approval. Eta Carinae is a reminder of this impermanence, inscribed across the sky in letters of light and dust. It is a star that has been burning for roughly 3 million years, a span of time that encompasses the entire evolution of our species, and it is about to stop. The atoms in its core, forged in a cascade of nuclear reactions over those 3 million years, will be scattered across dozens of light years of space in a matter of weeks. The structures it has built over its lifetime, the homunculus nebula, the wind collision zone, the complex web of magnetic fields and radiation that defines its environment, all of it will be obliterated in a flash of light and a wave of force so intense that it will reshape the local region of the galaxy. And then it will be gone, replaced by an expanding cloud of debris, and perhaps a compact remnant, a neutron star spinning in the dark, or a black hole swallowing even its own light. The glow of its explosion will travel outward at 300,000 kilometers per second, reaching star after star, planet after planet, eventually fading into the cosmic background radiation, indistinguishable from the faint, cold afterglow of the Big Bang itself. In a million years, there will be little visible evidence that Eta Carinae ever existed, save for the heavy elements it contributed to the interstellar medium and the faint, cooling remnant of its final explosion. This is the fate of all stars. It is the fate of our sun, which will one day exhaust its hydrogen fuel, swell into a red giant, large enough to engulf the inner planets, shed its outer layers into a planetary nebula, and leave behind a white dwarf no larger than the Earth, slowly cooling over trillions of years until it is indistinguishable from the black void around it. That event is roughly 5 billion years in the future, safely beyond the horizon of any meaningful human concern. But the principle is the same. All fires go out, all lights dim, all structures dissolve. What distinguishes Eta Carinae from the billions of other stars that will eventually share its fate is its proximity, its extremity, and its timing. At 7,500 light-years, it is close enough that its death will be visible from Earth without a telescope. Its mass is so great that its death will be violent in ways that standard supernovae cannot match. And the evidence suggests that its death may occur on a timescale that overlaps with human civilization, not in billions of years, not in millions, but potentially in thousands or tens of thousands, possibly even less. This convergence of proximity, power, and timing is what makes Eta Carinae so compelling and so unsettling. Every generation of astronomers, since John Herschel first documented the Great Eruption, has lived with the knowledge that this star could explode at any time. Every generation has trained its best instruments on the southern sky, watching for changes, looking for clues, hoping to understand, and every generation has been forced to pass the vigil to the next, the question still unanswered, the star still burning. There is something deeply human about this vigil. It speaks to our need to understand, to predict, to prepare, even for events that lie beyond our control and perhaps beyond our lifetimes. We monitor Eta Carinae not because we can do anything about its death, but because not monitoring it, not trying to understand, would feel like a fundamental betrayal of who we are. We are the species that wants to know, that needs to know, that cannot look away. And so we build telescopes and point them at the sky. We design instruments sensitive enough to detect individual photons from a star that lies more than 70 quadrillion kilometers away. We write software to analyze the data. We construct models to interpret the results. We publish papers, and argue at conferences and train new generations of researchers to carry on the work. And through all of it, the star burns on, indifferent to our attention, following the laws of physics toward its inevitable conclusion. The question of our place in the cosmos, raised so sharply by objects like Eta Carinae, has been a central concern of philosophy and religion for as long as humans have looked at the sky. Every culture has its creation story, every civilization has its cosmology, and every generation has grappled, in its own way, with the fundamental asymmetry between the smallness of human life and the vastness of the universe that contains it. Modern astronomy has not resolved this tension. If anything, it has deepened it. We now know that the universe is roughly 14 billion years old, that it contains roughly 2 trillion galaxies, that each galaxy contains hundreds of billions of stars, and that many of those stars are orbited by planets. The scale is so vast, so incomprehensibly large, that it defies any attempt at emotional or psychological integration. We can write the numbers, we can speak them aloud, but we cannot truly feel them. The distance between intellectual understanding and emotional comprehension is, in this case, as vast as the distances it describes. And yet there is comfort in the connectedness. We are not separate from the cosmos. We are not observers looking in from outside. We are participants. We are made of the same material as the stars. The hydrogen in our bodies was forged in the Big Bang. The carbon was made in a star. The iron was made in a supernova. We are the cosmos, organized into a pattern briefly capable of contemplating itself. And that pattern, fragile and temporary though it may be, is real. It exists. It matters. Not because the universe assigns it value, but because we do. And that is enough. There is a passage from the physicist Richard Feynman that captures something essential about this situation. He once observed that the beauty of a flower is not diminished by understanding its biology. If anything, it is enriched. The same is true of Eta Carinae. Understanding the physics of the star, the nuclear reactions, the gravitational dynamics, the mass loss, the binary orbit, does not diminish its grandeur, it amplifies it. To look at that faint point of light in the southern sky and know what it is, to understand the forces at work within it, to grasp the scale of its power and the inevitability of its end, is to experience a form of wonder that is available to no other species on Earth. It is a privilege earned by 300,000 years of evolution and 5,000 years of accumulated knowledge. And it is a privilege that carries with it a weight. The weight of knowing that what you are looking at is both magnificent and doomed. Somewhere in the constellation Carinae, hidden behind the veils of its own making, a star is dying. It has been dying for a long time. By human standards, the process has been excruciatingly slow, stretching across centuries and millennia, a patient unwinding of forces that have been building since the star first ignited 3 million years ago. By cosmic standards, it is happening with shocking, almost indecent speed. The nuclear reactions in its core are accelerating, each stage shorter than the last, each stage hotter, denser, more desperate. The hydrogen burning phase lasted millions of years, the helium burning hundreds of thousands, carbon thousands, neon years, oxygen months, and silicon, the final stage before the end, will last only days. Perhaps it is happening right now. Perhaps it has already happened. We cannot know. The light we see is old light, 7,500 years old, and the star we observe is a portrait, a memory, a ghost image of an object that may no longer exist in the form we recognize. The distance between observation and reality is unbridgeable. We look, and what we see is the past. We listen, and what we hear are the echoes of events that concluded before the first line of writing was scratched into clay. Eta Carinae is a monument to extremes. Extreme mass, 100 times or more the mass of our sun. Extreme luminosity, 5 million times the sun's energy output. Extreme instability, capable of expelling 10 to 40 solar masses of material in a single eruption and surviving. Extreme beauty, the homunculus nebula expanding at hundreds of kilometers per second, glowing with the light it absorbs from the central star, shaped into 2 perfect lobes by forces that we are still working to fully understand. A cosmic lantern, slowly growing in the dark, casting its light across 7,500 light-years of interstellar space. The 2 massive stars at the heart of this system orbit each other in a gravitational embrace that has lasted for millions of years. Every 5.5 years, the companion plunges through the primary's atmosphere, triggering a storm of X-rays and a cascade of interactions that ripple through the surrounding nebula. Each passage is a test. Each passage is a stress. Each passage tightens the bonds between the stars, even as it loosens the bonds that hold the primary's outer layers in place. And one day, whether in years or millennia, those bonds will break. The core will collapse, the star will tear itself apart, and the light of its death will race outward at 300,000 kilometers per second, carrying with it the news that one of the most extraordinary objects in the galaxy has finally reached its end. The story of Eta Carinae is, in the deepest sense, the story of the universe itself, compressed into a single object and played out on a timescale that is, for once, close enough to our own that we might actually witness the conclusion. It is the story of matter and energy, of gravity and radiation, of creation and destruction, of order emerging from chaos and chaos reclaiming order. It is the story of atoms forged in unimaginable heat, scattered across the void, gathering again into new forms, new structures, new complexities. It is the story of a cosmos that builds and destroys with equal indifference, a cosmos that does not mourn its losses or celebrate its triumphs, a cosmos that simply continues, driven by laws that were set in motion 14 billion years ago and will continue operating long after the last star has burned out. We are part of that story. The atoms in our bodies pass through stars like Eta Carinae, not this specific star, but stars like it, massive and luminous and doomed, stars that burned bright and died young, scattering their heavy elements across the galaxy, like seeds scattered by a dying plant. They burned, they died. They enriched the interstellar medium with carbon and oxygen and iron and all the other elements that make chemistry possible. And from that enriched material, 4.6 billion years ago, our solar system formed, our planet coalesced, and, over the course of billions of years of evolution, we emerged. We are stardust that has learned to think. We are the universe's way of examining itself. And when Eta Carinae finally explodes, whenever that may be, a new chapter in that story will begin. The heavy elements forged in its core over 3 million years of nuclear burning will join the interstellar medium. New molecular clouds will form, enriched with the products of its life and its death. New stars will ignite within those clouds, drawing on a richer palette of chemical elements than the clouds from which Eta Carinae itself was born. New planets will take shape around those new stars, rocky worlds with iron cores and silicate mantles and perhaps liquid water on their surfaces, and perhaps, in some distant future, on some world that we cannot imagine, beings that we could not recognize will look up at their sky and wonder about the stars that made them possible. They will not know the name Eta Carinae. They will not know that their atoms were once part of a hypergiant star in a galaxy called the Milky Way. But they will be its legacy. The cycle is ancient. It is as old as the universe itself, stretching back to the first generation of stars, the primordial giants that formed from hydrogen and helium in the first few 100 million years after the Big Bang. Those first stars, with no heavy elements to cool their forming clouds, grew to enormous masses, hundreds of times the mass of the Sun. They lived brief, violent lives and died in explosions that scattered the first heavy elements across the young cosmos. Without those first deaths, there would be no carbon. Without carbon, there would be no organic chemistry. Without organic chemistry, there would be no life. The first stars had to die so that we could live. And Eta Carinae, carrying on that tradition, will die so that something new can live. This is what the night sky is telling us, if we are willing to be still long enough to listen. It is telling us that we are temporary, that our world is temporary, that even the stars and the galaxies are temporary. Nothing endures forever. Not even the universe itself. If the current models of cosmic evolution are correct, the universe will expand and cool, the stars will exhaust their fuel, the black holes will evaporate, and eventually, in the unimaginably distant future, there will be nothing left but a faint haze of radiation in an empty, dark, limitless void. But the night sky is also telling us something else. It is telling us that the processes which created us are ongoing, that the universe is still building, still experimenting, still generating the conditions for complexity and consciousness. Stars are still being born, Planets are still forming, chemistry is still happening, and somewhere, on some world that we will never see, life may be taking its first tentative steps toward awareness. We are not the end of the story. We are not even the middle. We are a single word in a narrative that has no foreseeable conclusion. And so, tonight, if you find yourself beneath a clear sky, look toward the south. Look toward the constellation Carinae, toward the faint glow of the nebula where Eta Carinae resides. You will not see the star itself with your unaided eye. Not yet. The dust of the homunculus still hides it from view. But it is there, burning, fading, waiting, carrying in its core the seeds of future worlds and the power to outshine the galaxy. One day, perhaps in your lifetime, perhaps in your children's lifetime, perhaps in 100 generations or 1,000, a new light will appear in that part of the sky. It will grow brighter over the course of hours. It will outshine every other star. It will be visible in the daytime, a point of fierce, unwavering light in the blue sky that refuses to be ignored. And it will remain, slowly changing, for weeks or months, a beacon in the heavens, marking the place where one of the most extraordinary objects in the galaxy finally met its end. When that happens, if you are alive to see it, remember this. Remember that the light reaching your eyes has traveled 7,500 years across the void. Remember that the atoms being scattered across space at that moment are the same kinds of atoms that make up your body. Remember that your existence is not separate from this event, but is, in the deepest sense, a consequence of events just like it. Remember that the line between the star and the observer is thinner than you might imagine. We are the cosmos, briefly aware of itself, briefly capable of wonder, briefly here, and in the southern sky, a star is preparing to remind us why.